Testing, testing, 1, 2, 3. Testing, testing, 1, 2, 3. YouTube seems to be happy about the live stream. Cool. Hello again. So last time we finished number 1 and 2, get a virtual machine started using Cumin outputting to the screen, and number 2, getting a virtual machine booting with an RAMFS provided by TinyRange, starting with Alpine Linux. This is where we got to last time. As you can see, we can list files and do things in a virtual machine. That's really cool. But you probably would have noticed a few issues with this. SH, can't access TTY, job control turned off. That none, because as it turns out, our hostname is what hostname. And if we, the reason for that is if we look at our int script, it just logs this in as root. It doesn't do anything else. We could modify this init script just here to do more stuff. Like, if I just remember how to set the host name on Alpine. Yeah, so we just call this host login. And now it's called login. Cool, we've set the host name. But instead what we're going to be doing is we're going to be replacing this int process with a daemon that's going to keep on running on the system instead. That daemon's going to be written in Go, and it's going to be the first code that runs when the system starts up. It'll allow us to do things like networking setup. It'll allow us to do an SSH server, all other kinds of things that we'll eventually get to. But right now, first step is just get that daemon started up. So you may ask, why do we want to use the daemon? Can't we just use those int scripts? The problem is these int scripts are reliant on the root file system that the virtual machine already has. And we don't know what the root file system is going to be. Right now, we do. It's just Alpine Linux. But say we were to swap out Alpine with Ubuntu or Alpine with Fedora. Well, on a Fedora system, that login command isn't going to work the same. The hostname command isn't going to work the same. The SH isn't going to work the same. So for consistency's sake, we're going to be replacing this with our own separate executable. This executable doesn't have to be written in Golang necessarily. It could be written in C, but I've just found for ease of development purposes, writing it in Golang is easiest. So we're just going to call this init for now, and I'm going to do that. So we're going to need to recompile the init executable every time the system starts up. So let's create a quick build.sh shell script. Zoom bash, set ex, go build -o in bash set ex, go. Okay, go run. We actually just need this. Go build -o, build TinyRange, that, but we'll build go boot first. Well, we'll build out int executable first. We're not going to call it go boot this time because it's not actually a bootloader. Say int x86-64, since we probably want to add additional platform support in the future, additional architecture support for gas machines in the future. So ch1+x, build.sh, build.sh. Okay, so package main fmain org.info. Hello world! Yay. So now we have this init executable. Some other things we'll want to do with this. Export go os equals Linux, export go arch equals AMD64, export c go enabled equals 0. That was a whole bunch of stuff very quickly. Let's quickly show you what that change did, because this is important. Build.sh. So if we look in our build directory and we look at these executables, we'll see we'll see that the init executable happens to be statically linked. Cool. But our main TinyRange executable is dynamically linked. Why the difference between the two? Probably because Go detected that TinyRange is using CGO code, but the init executable, which isn't doing anything right now, is not. But if we force CGO to be disabled and we run build.sh again, and then we look at file again, all these, we'll see these executables are always going to be statically linked. The important thing about a statically linked executable on Linux is it'll run regardless of the distribution that you're on, because it comes with its own set of standard libraries. Unlike a dynamically linked executable, which, so for instance, that TinyRange dynamically linked executable, if I just undo that change again, and build this again. So my current TinyRange virtual machines are run Alpine by default. So if I go TinyRange login dash file TinyRange, we have a TinyRange executable, but if we try and run it, it's not found. Why is that? Okay, so this is the interpreter it's trying to run. Skipping through a lot of annoying details, if you try and run an executable and it says not found, it means that it couldn't find its interpreter for some reason or the other. So let's see if this interpreter exists. It doesn't. But, and that lib64 directory doesn't as well. But instead we have a lib directory with ld musil instead. And if we run file in busybox, we'll see that it's dynamically linked against musil instead. The implication of this is that on different Linux distributions, with different versions of the standard library, you can run into incompatibilities very quickly. So like, if we were to do this, because we're running on an Alpine system, it wouldn't work. Whereas a statically linked binary, even if there's no other system coming along for the ride with it, it'll still work. And actually, that's what we'll do next. So, so we'll build this again, and we've got this simple main that's in just prints hello world. We'll replace all of this create root file system stuff with something a little more simple. So all we're going to do is we're going to add that init executable that we just said into the system. Don't worry, at a later step, we're going to bring back a full Linux distribution into this, but for now, we're just going to have a single init executable. So, net read file input. If error is not to nil, return nil error. Error. Okay. Then init byte init. It's already a byte array, so I don't need to do that. Cool. So now we will make this instead local. instead of that, we will just say build init x86-64 build.sh and then build/TinyRange. You can see it exited immediately. That's because okay. Back to the same issue as we were having last stream, trying to figure out what's going on with our intrmfs. Okay. Let's mode perm. CPO short read. Let's just run a file to check that this is statically linked. It is. It's 64-bit Linux executable. In fact, we can actually run this on our host system. Just prints out hello world. Simple. So, why didn't this do anything? Let's revert most of those changes and init equal init os.read file. Okay. It was successfully able to run. So in which case that means it's probably missing some kind of item. The only thing that it could possibly be missing at that stage is the root directory. So and the root directory would default to having a modification time that's actually an invalid modification time. So if I just remove all of this stuff here, except, so it's that annoying mod time thing that we were running into previously. I never ran into this with my old code because it always just set the modification time to be a new time. So new directory should have a modification time time dot should have a default modification time of that. I called it M time instead of mod time. And I will make that change everywhere else just to make sure that we don't end up. Okay, that looks good. Yep, there we go. Voila. Yay, we can now print hello world inside of a Go program. Except now it's in our own virtual machine. I'm gonna add a few extra things to this, just for fun. So let's actually start up Starlark REPL. REPL. And then finally, globals is just going to be starlark.universe. And I will need to actually load that. Globals is starlark.string dictionary. Yep, and globals exit is a starlark.new built-in. That os.exit 0 and none. The operating system would have panicked. Well, the thread would be dead and the operating system would have panicked by the time that exit function gets called, but just good to have an exit function just in case. Go odd tidy. 2+2. There we go. I now have an extremely secure Starlark interpreter. And I can call exit and the virtual machine shuts down. If you want to run user code from a random website, that's probably a pretty good place to start. Good luck compromising the system. Firstly, you have to compromise Starlark, and then you're a privileged root user within a Linux system, so you could theoretically load modules and do things like that. So let's assume that the user can get up to kernel mode pretty easily. Okay, now you're in a KVM virtual machine running with Qum, both of which are very well secured. And that's probably the furthest you get. So you try and find a virtual machine escape. And then you manage to find a virtual machine escape. And then you made it to the host machine, but you're an unprivileged user. Good security. Why put Starlark for this? Why put Starlark for this int script? Well, because we're going to use Starlark as the main scripting for how we script virtual machine startup. This is just a kind of hello world test that gives us an opportunity to write a script. But we will, instead of just doing exit, we will actually run an init script that we create. So let's just create init.star fmain and print hello world. We need to get this init.star into the system, which conveniently is quite easy. We will embed this into the TinyRange executable for now. Init script by go embed init.star, and to use that we always have to do embed. There we go. Now we can. I don't really want it to be exported. Doesn't make a difference, but anyway. So we will add this file as well. Init.star, and its length is the same length as underline init script. Init script. And then in here we will use that same globals, but we will do thread starlock thread main init, and then decals error equals starlock exec file options set true while true level control true. Thread is that, file name is /init.star, and source is nil, and pre-declared is globals. Error nil. Fuck. Init name. Error. And we will just copy our same main function from over here. Oh, the reason that the virtual machine is immediately shutting down once we exit out of that is because we are the PID1. We are the init process. And on Linux, when the init process dies, it panics the kernel. And in this case, our kernel command line is set so that a panicked kernel will automatically shut down. Normally, with this configuration, the kernel would restart, but we also have the no reboot option passed to Hume, which will cause it to shut down instead. So we're going to call init main. Main func okay is decals main. You may remember from yesterday that this is pretty much the same exact structure that we're following for the virtual machine factory functions, which I believe is the callables just here. In fact, we can more or less do the same thing. Then error is starlock dot cool. Same thread is okay. It's the main function. We're not passing any arguments right now. We're not passing any keyword arguments. Goes complaining because we've already declared error. And if error is not equal to nil, return error, return nil. And cool, now we have hello world, but the hello world is being printed from starlock. Why do we do that? Because now we're giving the Go code on the host control of what's happening inside the virtual machine. Go code on the host can set it to whatever it wants. Where previously, if we wanted to change the behavior, we had to modify the init executable itself. This is pretty much all that I mean as far as write an init system is concerned. So on to the next step. I will just commit this quickly. So we actually want to ignore the build directory as well. Right. Status, right, git, commit -m, step 3, right, init system. So that's step 3 complete. Now step 4. Connect networking from the host to the guest using gvisor netstack. I'm going to take another few steps with this before I do that, because now is going to be a pretty good time to clean up this little bit of code, because we're going to need to start to pass some arguments around. So you will have noted that before our hypervisor script looks completely static like this, but let's make it so that we can specify our kernel and ctx.intrd. So if we run things as well, we can see virtual machine has no kernel field or method. So let's give it one. This is just, virtual machine doesn't even have attributes, so let's start out as attributes equals reference virtual machine. We're doing this because, I'll explain it more later, but in short, the way that the networking works is we establish a layer 2 tunnel between Cume and our host executable. And that tunnel won't always start up on the same port number, so we need to be able to specify the port number that's used for that. So we're going to do this by allowing the TinyRange executable to pass options into its hypervisor script that it's using. So string kernel, I just called it, yep, I just call it intrd, name equals kernel, vm.kernel, equals intrd. Simple. Else return okay. So we're going to have a kernel string and an intrd string. And then when we go to create the virtual machine, we'll set kernel string intrd string kernel intrd. And so we already know our kernel is this one here. and our entire RD is this one here. There we go. Runs the same thing. And I will also abstract this out a bit. VM.go. And let's just double check what our exports look like. Nice and clean. And yep, factory doesn't export anything more than we want it to. And VM exports a bunch of stuff, but that's just the standard style arc value. Alright, that's moved into a separate thing. Cool. Alright, now we are going to create a folder called netstack. And netstack docker. This is going to contain package netstack type netstack struct, and it's going to have a new function which just returns a netstack. Then over here we are going to do ns array equals netstack dot new. Does not return an error right now, and factory.create is also going to take a netstack. And I will just make sure we get the right import into that. I'm going a bit slow with this because honestly I've been putting off refactoring the way that my netstack code has been working in the old version of TinyRange for some time. It's going to be substantially more complicated than the code we were tackling yesterday. So, yeah. Netstack. Right. That works. So when it creates it, ns in this case just stands for netstack. ns is the netstack. And when we run it, we also set up a so we can't really dive straight into this. We're going to have to do a few little experiments first. So we're going to be using gvisor's netstack, which is pretty much the most popular piece of gvisor. Not surprising because which is, as I was saying, not surprising because it's a really stable, really battle-tested TCP/IP stack implementation that's highly accessible. Mostly, if you know how Google code works, which means it's also a pain to deal with. So I'm going to be, even after refactoring and optimization, all the code for NetStack in TinyRange is sat within a relatively large file. And even that, it has multiple sections to it. So there's the first part that we need that actually initializes the stack itself. Stack dot new. So ns is net stack, and stack is stack stack. And yep, that's correct. So we want to do go get. If you just get the gvisor repository directly, it doesn't work. You have to use a synthetic branch called go instead. If you don't do this, then you'll get weird to trace back compile errors. But since I did remember to do this, this should work fine. Like standard Google, this is quite a lot of code. It also has a lot of breaking changes associated with it. Okay. That's just saying they didn't use the GitHub name, they used their own. There we go. That now works. Okay, that now works. Sweet. So then we have the network level initialization that needs to happen. This is again a lot of relatively ugly code that I'm going to write first and then going to try and debug. Function star stack init. Return an error. So go back up to main.go and if error ns.init return error. So this will initialize the net stack. Thing is, I forget out of all of this what parts are important and what parts are not important. So gvisor is. So okay, explaining briefly what gvisor is. Gvisor is a application level hypervisor. That's a whole lot of fluff, but the simplified term for it is Google went and re-implemented basically the entire Linux kernel in Go. And then they just run all the applications inside of it pointing at their own kernel written in Go instead of the normal Linux kernel. And then gvisor in turn translates the requests made by regular applications to requests made to the underlying host Linux kernel. As part of that, it has a network stack. The network stack behaves very similar to a regular Linux network stack, where it has multiple network interfaces. Where it has multiple network interfaces, and all of those network interfaces can do standard TCP/IP stuff on top of them, which is all in all very cool. So, where does this get complicated? And also, why are we doing this in the first place? So, how do we do virtual machine networking? Two ways. So, virtual machine, when it's sending traffic, wants to behave as if it's attached to a virtual Ethernet cable. That virtual Ethernet cable is plugged into the virtual machine, it sends traffic over that cable, and that cable is connected to whatever else is going on. It's not a physical cable, it's a virtual cable. The normal way of doing that is to use a ton interface, I believe is the right name. A ton interface so there's one called ton, there's one called tap. Ton is level 2, ton is layer 2, tap is layer 3. Foreshadowing. So say ton is the layer. I'm actually just going to quickly search this to make sure I'm doing it right. Tap. Tap. Yes. So we have a ton interface, which is like a tunnel. It carries IP layer packets. We have a tap interface, which carries Ethernet frames. The virtual machine spits out layer 2 Ethernet frames, and it expects, and then those go into the host kernel through the tap device, and then the host handles all the routing for it. A tap device on the host allows you to inject layer 2 traffic, which the host interface will then process. This is how this is done normally. It's very fast, very performant. If you see virtual machines doing networking, this tends to be the way that they're doing it. It's not suitable in our instance, though. Number one, it's operating system specific. The interface for doing for sending things on a tap or tunnel is different on Windows, macOS, Linux, every other operating system. We don't want to have to re-implement our entire networking stack for each operating system we want to support on the host. That's a bad idea. Number two, it's privileged. If I, on my host Linux system, try and create my own tap device, it'll just say, no, you're not allowed to do that. Sorry, you're not root. There are clever ways around that. The unshare command. Look, I am now root. I didn't have to enter my sudo password because I didn't even have to have sudo privileges to do this. I could go on another system and do it myself. If I have a look at the network configuration of this, we'll see, oh, where did all my network interfaces go? This is my host machine. This is the machine that the stream is coming from. So yes, the host machine is connected to the internet. But we can do something like IP link set hello up. Cool. Now we have a loopback. We just did that as an unprivileged user. We can now add tunnel devices as an unprivileged user. We can connect them all up. We can do networking all as an unprivileged user. Great. But it's Linux specific and only works if you have user namespaces enabled, or if you're running as root. If you're looking at like a Docker, or if you're looking at libvirt, other things like that, they're all running as root. Docker does have the capability to not run as root, but yeah. So what we're going to do instead is tell Qum to talk directly. Instead of talking to the kernel, we're going to tell it to talk to a tap device inside of gvisor instead. Perfect. Here's where that foreshadowing comes in. And this is what's going to make the implementation slightly more complicated. I could save this for later, but let's just go up front. gvisor does not support tap devices. gvisor does not operate at layer 2. It operates at layer 3. I can create a ton device, but Qum operates at layer 2. So I will need to handle the routing and translation of layer 2 to layer 3 traffic myself. I've done this before. It's a bit of a pain to set up, but it's doable. Also, the other reason why we're going through all this is it'll allow us to run like our own DHCP and DNS server for the virtual machine as an unprivileged user, which is really cool. That's why we're going through all of this suffering. So now, to continue with the suffering. So Cume's network interface stuff. We're going to assume that we're using VirtIOnet, which means we're going to be doing -netdev socket id equals net udp equals thing local address equals thing dot format ctx dot net send net receive and dash device and dot format. Okay. Now we have a little bit more stuff on here. This net send and net receive, they are both UDP addresses. So what this means is that Cume will send traffic out on UDP, and it will expect to receive traffic in on UDP that's being sent to it. It's all really cool. And Cume will do this all by sending layer 2 packets. So so the first step that I'm going to go through with this is actually seeing if we can receive those layer 2 packets, because then we need to start doing processing on them. So when the virtual machine goes to actually if we run this again, we don't have a net send or net receive. Else name equals net send. Else name equals net receive. Equals map address. And string nick net send. So now we'll have a network interface. Let's send string, receive string, and map. And we will have a function as netstack attach network interface. And essentially here we need to return a network interface. Interfaces is an array of network interfaces. And then network interface. If we try this now, then we will see that our nick is nil. No, let's fix that quickly. Nick error vm dot ns dot nil return error. Nick equals nick. Okay. Now we're just getting errors because those things are null. So when we go to attach a network interface, We have one UDP socket that's for sending. We have one UDP socket that's for receiving. So that means we first need to listen for UDP socket. So net dot listen UDP thing is P is net dot files IP 127.0.0.1 and just have to make sure I'm getting this the right way around. So net send equals receive dot local address dot string. Yep. That should be good. Should probably also test that as well. Yep, that looks good. Now we just need to listen for another one. I'll just call this send. Address. And nic.net receive equals receive dot local address dot string dot close. And then we immediately close it, so Cume can open once again. Now we also need to specify a MAC address, and we also need to make sure that the sender is actually doing something. Read. I'm just going to look in my code to make sure that I'm getting those two correct. Oh, for loop, of course, and also have a UDP connection, which is a connection. There we go. And that should pretty much be it. And we'll also just add it to the interfaces list. Interfaces.append. Okay. Oh, and we also need to set a MAC address. MAC address equals I tend to just have a little helper function that I copy pasted from Stack Overflow that I use to generate MAC addresses. Note that this always generates MAC addresses with those first 3 bytes set to a default number, and also always makes it a local address. Okay, so you can see that we've got the virtual machine actually started up. That's great. The next step for this is we're going to want the virtual machine to initialize its networking stack. So we're just going to make a little quick function here called network interface up. Hello, and interface up, ETH. We'll bring the loopback interface up, and we'll bring ETH0 up. Easy. And we will go back to the main function here and implement those. Go back to the main function here and implement those. So globals interface up equals starlock built-in interface up. And script 1. As soon as we bring this network interface up, it should start doing things, which will be enough for us initially. We'll want to actually try and send some traffic next, but yeah. Main string and args kwargs. Let's just grab this RTNL library. This library allows Go to talk directly to the Linux kernel and make changes to the Linux kernel's network interface. And allows it to make direct changes to the kernel's network interfaces. Yep. So we brought allo0 and ETH0 up. We can see that if we were to do a different thing, that we are actually bringing the correct interface up, and we will now do a network interface configure ETH0 IP address is 10.42.0.2. And the subnet mask for that is a /16, and I'm just going to refer quickly to my old S3 night. Yep. Good news, I get to copy all this code. Oh, and I also realized that this is slightly smaller than what I had before. There we go. Actually makes it a little bit easier for me to read as well. This is probably because of that. Right. This is actually using a DHCP library. Spoilers, we will be continuing to use that DHCP library. So what did we see? We said that we configure the network address statically. Cool. And now we'll do a contents equals fetch HTTP 42.0.1. Hello. And now we will add a locals fetch equals very similar style arc built in. That will work in much the same way. So this will take a URL, it'll be URL string, and it will do resp error is http.get URL string. Error is equal to nil, turn error. Rest.body.close. Contents. Error is IO. Read all. Body. Error. And then return string contents. No. Okay. You'll see that. Ooh, we got some packet data. We got some packets. That's nice. Quite like a proper hex dump of the packets though. We got some packets from the guest. Now we need to actually do something with those packets. These packets are probably the virtual machine asking the host to see if it, probably the virtual machine doing a broadcast out to figure out the MAC address of the host machine. That's pretty obvious because these first 6 bytes are all FF, and then these next ones, I believe, are the MAC addresses that we're generating. Yep, 88. I'm assuming that's 75, and then the next one is 0x56, and 0x56 is a capital V, 0x75 is a lowercase u. So that's our MAC address. Then the rest of it is what the virtual machine is doing. So now we actually need to do something with this traffic. So we will just keep logging that, but we will also send it. So on receive packet. So we will have an on receive packet method that just takes the slice that is the packet itself. Also make sure to print out the errors, and this method's probably useless after that returns an error. So we now have a func ns net stack on receive packet byte. Okay. So here's where we go back. So as well as setting a net stack, we're also going to create a host channel. Oh no, we're not going to create a host channel just yet, because I'm probably going to refactor that. So, like I said, we can see with these packets how they contain the MAC addresses in them. These are layer 2 Ethernet frames. Ethernet frame format. we, in this case, do not get a destination MAC address, do not get a preamble or SFD, but we do get a destination MAC address, which is the first one, and a source MAC address, and then we also get a ether type. The ether type looks to be /b. So ether. So okay, so we have a source MAC equals net.hardware address kt the 6 bytes, and then source MAC, which is the next 6 bytes. Okay, so we can see that this is targeted at a broadcast, and we can see that the source MAC address probably changes each time because we of course randomize all of that data. And ether type is binary dot Ethernet's always big Indian dot uint16 pkt 1214, and then payload is PKT4 is everything after PKT14. So ether type is ether type, and payload is payload. So we'll see ether type of this is 254, which I can already see is up. So if proto TCP IP dot network protocol number, if ether type is equal to ARP dot protocol number, then proto is ARP dot protocol number. Yes, if ether type is equal to IPv4 dot protocol number, then proto equals IPv4. And again, the reason that we're having to do this is because a gvisor doesn't handle layer 2 traffic, so we're having to decode the layer 2 framing ourselves, which is what this is doing here. And else s log warn net s and then protocol number. And then we also make a packet buffer, which is just the payload. Which is what I previously did. So this packet is successfully parsed now. So we can just do inject inbound on a channel now. So now we actually need a channel. So we're actually going to move this on receive packet function into a particular network interface. This is the big change I'm doing here, because it probably this means that each virtual machine pretty much gets its own separate ton device, more or less. So that's just going to be nick.onReceivePacket. And the nick is going to have channel star channel dot, yep, which is just a channel dot endpoint, channel dot endpoint. And then when this gets created, nick dot channel equals channel dot new. I need to remember the parameters I passed to this. Host MAC equals generate MAC address. I'm going to make this function slightly less cursed and have it return a net.hardware address instead. Beforehand it just returned a string and y. So it is typically a 6-byte MAC address. In which case, that's exactly what it is. Host channel size and host channel NTU. These kinds of parameters are actually pretty important for tuning. And these numbers come from previous pain and suffering that I luckily don't have to deal with again. So from a networking perspective, we're building something a little different than what I had before. Beforehand, I had a router system that was doing all the recording of a MAC address. In this case, what we have is every virtual machine is going to be connected to the host on a network interface. So each virtual machine gets its own separate network interface. That should dramatically simplify this code. And that's part of the reason why I'm doing this rewrite in the first place. It also means that, for instance, I could have like a WireGuard. I could have a WireGuard VPN tunnel on one of these network interfaces, and then that WireGuard tunnel would be able to talk to other virtual machines. Or I could have some other kind of tunneled connection with other instances of TinyRange connecting to these virtual machines, or without system administrator privileges. Like you'd be able, using WireGuard, you'd be able to give these virtual machines unrestricted internet access effectively without having root on your host, which is kind of cool. You just need root on the other host where WireGuard's set up, but just purchase some VPN service like whatever that supports WireGuard. Voila. So device MAC nic.MAC address equals device MAC.string. Simple. So we've got packet buffer and channel.inject inbound. Protocol is proto and packet buffer. There we go. Still doesn't do anything. But we're getting closer. We've now got a channel created, so we have to do something with that. But first, I'm going to go and do something for 10 minutes. Back. All right, where was I? So we've created the channel. So we also need to, on the ns.nstack.create nick. And we need to attach the channel to that. For whatever reason, Google, the makers of Go, decide to create their own custom error type, which nobody else does in Go. Ah, so annoying. Is the error type that they created even compatible with a regular error? No. Okay, apparently there's a loss of information problem. It'd be nice if they documented that a little bit more. Next, nick ID. I've probably done thousands of runs of TinyRange, and I don't run into those kinds of errors very often, so I do not expect to be running into them now, but just in case. And at the end of this, next nick ID plus equal, yay, ns.next nick ID. It's actually tcp/ip.nick ID. That enables forwarding for the nick ID. That assigns a protocol address for it. Prefix length is currently 8, but let's just make it 16 instead. Remind me how address from slice works. Okay, 10.42.01. Who knows? This may come up with an error if I have multiple virtual machines attached. And this sets a default route. Do I actually need a default route? I'm not sure. But this should configure to have all of this running inside of it, which means we get a subfault. Which probably means that the ns.net stack is not initialized yet, but we do initialize it. We don't really need an init function, so let's just delete you. So it's doing create nick with option, which is doing create nick. Which is doing ns.nstack, which happens when it runs the virtual machine. it does have a net stack created. So info ns. Net stack is nil for some reason. Oh. TCP/IP error at nil. Okay. So ooh, we're getting an error with this. Invalid NIC ID. I think we're not allowed to have a NIC ID of 0 for some reason. So I'll edit up the top. Okay? We are getting packets. So let's now see if what happens if we start to pull packets out. So that means go func to do. We do for loop. So we do nic dot channel dot read. PKT is nic dot channel dot read. Packet PKT dot packet from host. It's nil for some reason. Oh. Because you need to do read context. Got packet from host. Ooh. The host is giving us packets. Wonderful. So now we need to generate one of these packets for the client. So to avoid memory leaks. To avoid memory leaks and other issues, we do need to decrease references. Again, why all of this is so complicated, I'm not sure, but it's good. So, interesting. PKT.as slices. PKT bytes is equal to, do we know the packet size? Yep, we know the packet size. We want to make byte, which is packet size plus the size of an Ethernet header, which is 14 bytes. And then we'll call this packet bytes for slice lanes packet as slices. This equals slice range packet slices. Packet bytes. Packet bytes. our code had a lot of big, very complicated processing for all of this. Turns out it's not necessary. So for the layer 2, we have the destination MAC address first, which is the device MAC address, which I will put just here. And so copy device MAC. The destination is packet bytes 6, and the source is device MAC. Copy is just a mem copy. And copy packet bytes 6:12 is going to be our host MAC address. It's going to be our host MAC. Then copy PKT bytes 1214 is binary dot big endian dot put uint 16 pkt dot network protocol number. So we're putting the network protocol number into that, and making sure that this is casted into uint 16. Offset is going to start at 16, and then off plus equal copy bytes off slice. Okay, so this will just copy and construct everything nicely. Right, we get a packet from the host that looks like the correct packet. Once the VM gets this, good things should happen. Hopefully. Maybe. Okay, so what we do to send this to the VM is very simple. nic.udpconnection.write. And it's just packet bytes. If error is not equal to nil, small dot error failed to write packet to guest. Okay, that side of things is pretty much to be expected, because we're expecting the virtual machine to talk to some web server, so we actually need to implement that web server. So what we will do is I will have a func ns star net stack listen internal, which listens on an internal address, takes a network string and a address which is a string, and then returns a net.listener and an error. So nil. This is not yet implemented. And we will do listen error ns dot listen internal listens on TCP (0.0.0.0:80) Yeah, we're running as a non-privileged user, but because we're controlling our own network stack, we can listen on whatever ports we want. We can do whatever we want. None of this will have any impact on the host. So I want to do go func, and then http dot serve listen, and handler is box http dot new serve box, and it listens here, and serve. Mux.handle func. If you receive a request /, then w.write hello world /n. Not implemented, actually, because we haven't implemented this listen internally yet. Guess what? I'm going to cheat yet again. This is the benefit of having already written most of this code. Okay, that's going to be slightly more complicated. What's happening here is that we haven't yet added the protocol address for the specific NIC yet, which we probably need to do on an initialization step. Yeah, we probably... Like I said before, we're effectively creating a tunnel device that is being used by Cume. So we have the choice of doing this properly or doing a crazy little hack. I'm gonna go with a crazy little hack for now. Because if we do time.sleep, 100 times time.millisecond, then this will work. I would say that would be working, except that it's not. So my question is, what even are these packets in the first place? Which I'm gonna have to do some Wireshark shenanigans to do. The best way to do this is to have a is to have a packet dump for this. Stack. Alright. Write packet capture to writer, which is an io.writer. Error. So ns.packetDump equals writer. So I will just call a so for the net stack itself, packet dump is going to be a pcapgo.writer. I'll do Chrome Tiny to pull in this stuff. And then whenever we get a packet, it may be because I'm not yet setting a default route, which is something I'll try with this after. If ns.packetdump is like nil, and write packet there. It also needs to do and return nil. We won't call this write packet capture, we will call this open packet capture. And then back at main, we will do equals create local network.tcap. Error for f to close, then if error is ns dot packet capture with f to nil, return error. Right. Right. We should now have a packet capture, so I will just go into that directory and have a look at the packet capture. I don't think this will not be visible on stream, but shouldn't be that simple. Well, it shouldn't be that complicated. It's attempting to do ARP resolution, which means I probably need to have a look at how I did my ARP code, just to see if there's some complexity with things. Okay. So I'm definitely getting something back that's supposed to be some kind of ARP traffic. Range login. TinyRange has the ability to do packet captures as well. They're very useful. Okay, so if I now compare these two ARP things. Okay, looks like it's pretty much correct. Looks like it's pretty much correct, but I'm just emitting the packet wrong. So that means that my logic which is further down, I believe, here, it's detecting that it is actually the correct type. Oh, I set offset to 16, offset should be 14. Off by 2 error. So annoying. Okay, that's more interesting result. So if we look at that, then we're getting TCP SYN. We're getting a TCP SYN, so the ARP response is now working, but we're not getting any ACKs back. That probably is just because I don't have the default route set up. So all the default route does is all the default route does is this. Error. Oh, look, a whole lot of nothing. Hello world! Oh, wow! And now we have a whole bunch of packet debugging stuff. So if we comment those out, we get hello world! Yay! We can now send traffic between the host and the guest. Oh, I honestly expected that to take longer. Wow. Nice. Yeah, I honestly expected that to take longer. I don't know what to say. It's only 2 hours into this stream, and I guess we've already got networking working. And in an implementation that is substantially shorter and simpler than my old implementation, which is a really good outcome, although I'm still missing a number of different, like, as well as listen internal, I also have like listen packet internal and dial internal and stuff like that, so you can establish connections. We will do that next time when we write a DHCP DNS server and then switch from using stood out from QEMU to SSH. Yeah. Next time we may well just try doing 5, 6, 7, and 8, which will give us the ability to boot quite a lot of stuff. Or maybe at least 5, 6, 7. Pulling images from OCI repositories actually involves a fair amount of code, and maybe that's a next time thing. But yeah, I suspect I will not stream tomorrow since I have stuff on in the evening, but day after, yes, definitely. Maybe starting a bit earlier so I can go a bit later. But yeah, that's successful. So yeah, briefly, the implication of this is we have now got a web server on our host machine that is just a regular Go web server that we can make requests from inside the guest. So if we look at the init.star, we are doing this fetch HTTP. We could do any request and use this to request files from the host. We can do WebSockets. We can do whatever we want over this. The fundamentals of this code is something that I've been using inside TinyRange for a long time, and it turns out to be really reliable for most applications. Some applications it has problems with, but those are later things for us to work on. Yeah, this is super cool. Awesome. Thanks for watching. Bye.